NASA, meanwhile, has successfully averted a big problem. Its engineers had sent a wrong signal to Voyager 2 and had lost contact for nearly about 10 days. But the US Space Agency has said that it has successfully reconnected its space probe.
The story begins with an extraordinary launch, the moment a meticulously designed machine embarked on a groundbreaking mission. Voyager 2 was not just any spacecraft. It was humanity's first emissary to the outer planets, a silent observer tasked with unraveling the mysteries of distant worlds beyond imagination. Its ambitious trajectory carried it past the gas giants and icy moons, revealing alien-like environments that challenged perceptions of our solar system. The data returned to Earth transformed humanity's understanding of these remote worlds. Voyager 2 unveiled Jupiter's raging storms, Saturn's intricate rings, and Neptune's supersonic winds. Yet, among these remarkable discoveries, its fleeting encounter with Uranus, the least explored of the gas giants, left behind the most profound enigmas. Secrets encoded in Uranus's magnetic field, its moons, and its peculiar tilted rotation hinted at complexities yet to be fully understood. Though Voyager 2's journey ended decades ago, its findings continue to echo in today's scientific inquiries. By revisiting its data with modern technology and fresh perspectives, researchers are uncovering insights that Voyager itself could never have predicted. The spacecraft's historic flyby of Uranus in 1986 marked a pivotal moment in humanity's exploration of the outer solar system. For the first time, this distant and enigmatic planet, with its blue-green hue, faint rings, and unique rolling ball-like rotation around the Sun, was closely observed. Beneath the captivating images and data, however, lay puzzles that demanded further scrutiny. The magnetosphere of Uranus, in particular, has become a focus of renewed investigation. During Voyager's approach, an unusual and intense burst of solar wind, a high-energy surge of charged particles from the Sun, compressed Uranus's magnetic field to just 20% of its typical size. Such extreme conditions occur only about 4% of the time. Had Voyager arrived a week earlier, it would have encountered a more expansive magnetosphere, resembling those of other gas giants like Jupiter and Saturn. This rare solar event led to an initial misinterpretation of Uranus's magnetic environment. Early analyses suggested that the planet's magnetosphere was unusually weak, with sparse plasma and highly energetic radiation belts. However, plasma, a state of matter where atoms split into charged particles, is a common feature of magnetospheres surrounding planets with strong magnetic fields. The new findings reveal that the solar wind's intensity likely suppressed the presence of plasma, creating the false impression that Uranus's magnetosphere was unusually barren. Recent research published in Nature Astronomy has corrected this perspective, suggesting Uranus's magnetosphere is more typical of a gas giant than previously thought. This reevaluation extends to its moons, Titania, and Oberon. Voyager's initial observations placed these moons outside Uranus's magnetosphere, but new analyses propose that they are likely enveloped within this protective magnetic bubble. This revelation has significant implications for the potential existence of subsurface oceans on these moons, an area of growing interest as scientists search for life in the outer solar system. A closer examination of solar wind reveals its profound influence on planetary magnetospheres. When charged particles from the Sun collide with a planet's magnetic field, they exert dynamic pressure, leading to compression, expansion, or reshaping of the magnetosphere. This interaction is far from static, as the solar wind's intensity fluctuates based on solar activity and the planet's distance from the Sun. Planets with robust magnetic fields, such as Earth, Jupiter, and Saturn, experience significant solar wind effects. Their magnetospheres, shaped by internal magnetic fields, act as protective shields, deflecting and redirecting charged particles to safeguard the planet from harmful radiation. However, this defense system is not impervious. The size and strength of a magnetosphere are directly influenced by the solar wind's dynamic pressure, which varies in density and velocity. During Voyager 2's historic flyby of Uranus in 1986, the spacecraft encountered extreme solar wind conditions. At that time, the dynamic pressure of the solar wind, determined by its mass density and velocity, was at an extraordinary peak. Under typical circumstances, Uranus's magnetosphere would extend 22 to 25 planetary radii from the planet. However, as the solar wind pressure intensified, the magnetopause, the boundary balancing the solar wind's pressure with the planet's magnetic field, compressed significantly to just 17.3 planetary radii. This compression dramatically altered Uranus's magnetosphere, impacting not only the magnetopause, but also the planet's radiation belts. Ordinarily, radiation belts around planets form from plasma sourced from the planet's atmosphere, its moons, and the solar wind. However, the heightened solar wind during Voyager 2's approach likely expelled plasma from Uranus's magnetosphere, leaving it depleted and modifying its radiation belt dynamics. One striking consequence was the appearance of an unexpectedly intense belt of electron radiation, which puzzled scientists for decades. Only recent findings, unveiled in October of this year, have begun to clarify these phenomena. Voyager 2's data also highlighted Uranus's highly tilted and offset magnetic field, initially interpreted as evidence of an extreme and unique magnetosphere. Yet, further research suggests that this initial assessment did not fully capture the planet's complex cosmic dynamics. The compression of the magnetosphere triggered a cascade of dynamic processes. For instance, the increased solar wind pressure likely injected hot plasma from the magnetotail into the inner magnetosphere, a phenomenon also observed on planets like Saturn. On Saturn, solar wind compression events amplify kilometric radiation and trigger magnetic field reconfigurations. A similar occurrence at Uranus likely intensified its electron radiation belts and altered its magnetosphere's plasma composition. These events parallel geomagnetic storms on Earth, where magnetospheric compression enhances electron radiation levels. Interestingly, Uranus's magnetosphere under these intense conditions began to resemble those of other giant planets like Jupiter and Saturn. The compressed magnetosphere likely charged the radiation belts, while changes in the magnetotail dynamics, such as magnetic reconnection, may have further ejected plasma into the inner magnetosphere. This process, well documented on planets like Earth and Saturn, causes plasma density shifts and heightened radiation levels. For example, similar events on Saturn have been linked to enhanced radiation belts and intensified auroral emissions. In Uranus's case, the increased radiation likely triggered significant alterations in its magnetosphere, offering new insights into its behavior under extreme solar wind conditions. These findings have reshaped the understanding of Uranus's magnetic environment, revealing it to be more dynamic and interconnected with solar activity than previously thought. While a substantial body of data exists on the behavior of magnetospheres under compression on other planets, Uranus presents a unique challenge. The planet's pronounced axial tilt and distorted magnetic field introduce complexities that make its magnetospheric dynamics particularly intriguing. These peculiarities may lead to distinctive configurations, potentially influencing the intensification of electron flux and the unusual behavior of Uranus's radiation belts. Recent studies revisiting the dynamics of Uranus's magnetosphere have highlighted the importance of understanding how these conditions might affect the potential existence of subsurface oceans on the planet's moons. Among Uranus's moons, Titania and Oberon have long fascinated researchers, particularly regarding the possibility of hidden oceans beneath their icy exteriors. These moons orbit Uranus at distances of 17 and 22.8 Uranian radii, placing them in a distinctive position relative to the planet's magnetosphere. For moons closer to Uranus, such as Miranda, Ariel, and Umbriel, subsurface oceans can be detected through magnetic induction, an interaction where Uranus's magnetic field generates currents in conductive layers within the moons, producing detectable signals. However, Titania and Oberon were previously believed to spend significant portions of their orbits outside the magnetosphere, near the magnetopause, the boundary where Uranus's magnetic influence meets the solar wind. This assumption posed challenges for detecting subsurface oceans, as magnetic induction measurements become impractical in such conditions. New simulations, however, challenge these earlier conclusions. Data now suggests that Titania and Oberon likely remain within Uranus's magnetosphere for most of their orbits. Titania has less than a 4% chance of crossing the magnetopause, while Oberon's probability is slightly higher, around 13%. This revised understanding reveals that both moons spend the majority of their orbits within the protective magnetic bubble of Uranus. As a result, the potential for using magnetic induction to detect subsurface oceans becomes far more feasible, opening exciting new possibilities for exploration. These findings also have significant implications for the interactions between Uranus's magnetosphere and its moons. Within the magnetosphere, the moons encounter plasma dominated by the planet's magnetic field rather than the more turbulent plasma environment of the magnetosheath. This distinction reduces disruptions to magnetic induction measurements, enhancing the likelihood of identifying subsurface oceans on Titania and Oberon. Science is a process of continuous discovery, where new data refines or overturns previous assumptions. Uranus exemplifies how emerging evidence reshapes understanding, prompting fresh investigations into the unknown. To truly grasp the mysteries of this distant world, a future orbital mission equipped with advanced technologies is essential. Continuous high-resolution data from such a mission could provide critical insights into Uranus, its moons, and its rings. As plans for future missions to the Uranian system take shape, understanding the dynamics of Titania and Oberon's positions within the magnetosphere becomes crucial. Knowledge of the solar wind's variability and the magnetosphere's behavior will guide mission trajectories, ensuring optimal conditions for data collection. Magnetic induction techniques, already successful for icy moons like Europa and Enceladus, can now be confidently applied to Titania and Oberon. A dedicated mission to these moons could deploy magnetic sensors to explore their internal structures, seeking evidence of liquid water beneath their icy shells. The push to explore the outer solar system is gaining momentum. In 2022, NASA's decadal survey prioritized an orbital mission to Uranus, reflecting growing recognition of the need to study ice giants, enigmatic worlds that remain largely unexplored. Such a mission could fill critical gaps in understanding, not only illuminating Uranus and its moons, but also expanding humanity's knowledge of the diverse and dynamic environments within the solar system. The upcoming exploration of Uranus is set to transform humanity's understanding of the outer solar system. A highly anticipated mission, currently proposed for launch in February 2031, aims to arrive at Uranus by 2043. This spacecraft will focus on unraveling the complexities of Uranus's plasma environment, magnetic fields, and heliophysical interactions, offering invaluable insights into the dynamic processes that govern ice giants. With a dry mass of approximately 1 ton, the spacecraft will also gather data on Uranus's atmosphere and rings, marking a significant step forward in planetary science. The launch window for this ambitious mission extends from 2030 to 2034, providing flexibility in execution. China is also entering the race to explore the ice giants with its Tianwen-4 mission, scheduled for launch in 2030. This bold initiative will carry 2 spacecraft aboard a Long March 5 rocket, one destined for Jupiter's moon Callisto and the other set to conduct a flyby of Uranus. While smaller in mass compared to NASA's proposed mission, the Chinese spacecraft will be equipped with sophisticated instruments to study Uranus's magnetosphere and other features. Utilizing gravitational assists from planetary flybys, the mission will chart its path into the outer solar system, exemplifying international efforts to expand humanity's reach among the planets. The achievements of the Voyager missions laid the foundation for these ambitious endeavors. Voyager's journey through the outer planets not only expanded scientific knowledge, but also inspired generations of explorers. Today, the quest to understand the cosmos continues, driven by humanity's relentless curiosity. Each new mission builds on the legacy of past discoveries, forging a deeper connection to the universe. Amid the stars and galaxies, a recent discovery has captured the imagination of scientists. A faint radio signal, originating from a star system just 12 light-years away, has been detected. This system, centered on a star known as YZ Ceti, holds a remarkable secret: the potential presence of a magnetic field around an Earth-sized exoplanet in orbit. Such a magnetic field, akin to the one shielding Earth, could have profound implications for the habitability of distant worlds. What does this signal mean? Could this exoplanet resemble Earth more closely than previously imagined? And what might it reveal about the search for life beyond our solar system? Radio signals in space, sometimes referred to as whispers from the cosmos, are a form of electromagnetic radiation, traveling vast distances at the speed of light. These signals, generated by stars, galaxies, and even planets, carry valuable information about their origins. They can reveal the composition of stars, the presence of exoplanets, and even clues about the birth of the universe. To detect these signals, scientists rely on radio telescopes, such as the Very Large Array in New Mexico. These instruments, acting as ears to the universe, are designed to pick up and analyze faint radio waves. Once detected, signals undergo rigorous analysis using advanced algorithms and computational models. This process provides detailed insights, including the signal's location, distance, and physical properties. Radio signals from space are more than a scientific curiosity. They play a critical role in modern life. These signals are the backbone of GPS navigation, weather forecasting, and Earth observation, seamlessly integrating into the technological infrastructure of the modern world. Yet, beyond their practical applications, these signals tell a profound story, a cosmic conversation, an orchestra of electromagnetic whispers echoing through the universe, waiting to be understood. In the vast expanse of space, within the constellation Cetus, lies a star that has captured humanity's attention. This star, known as YZ Ceti, resides a mere 12 light-years from Earth, a close neighbor on a cosmic scale. YZ Ceti is a red dwarf, smaller and cooler than the Sun, but its true intrigue lies not in the star itself, but in the planetary system that orbits it. At least 3 exoplanets circle YZ Ceti, with one, YZ Ceti b, standing out as a focal point of recent discoveries. YZ Ceti b is a rocky, Earth-sized exoplanet that orbits perilously close to its parent star. Its year, the time it takes to complete one orbit, is a mere 1.6 Earth days. Recently, researchers using the Very Large Array made a groundbreaking discovery: a repeating radio signal emanating from the vicinity of YZ Ceti. Detected at a frequency of 2 to 4 gigahertz, the signal appears modulated by the star's rotation and the planet's orbit, suggesting an interaction between the planet's magnetic field and the stellar environment. This finding, led by scientists at Bucknell University, carries profound implications. While YZ Ceti b itself is unlikely to harbor life due to its extreme proximity to its star, the detection of its magnetic field is a milestone. It offers a potential method for identifying exoplanets with magnetic fields, an essential characteristic for planets that might support life. Magnetic fields are vital components of planetary habitability. They shield planets from harmful radiation, protect atmospheres from being stripped away by stellar winds, and contribute to the stability of conditions necessary for life. Earth's magnetic field, for instance, is crucial to maintaining a stable environment, while the Sun's dynamic magnetic field governs solar activity, influencing phenomena like sunspots and solar flares. Even on a galactic scale, magnetic fields guide the motion of interstellar gas and the birth of new stars. If you enjoyed this journey into the unknown, Don't forget to like, share, and subscribe to our channel. Join us as we continue to explore the wonders of the universe, one discovery at a time. And as always, keep looking up. The universe awaits.